Okay, good. So here it's concave down, here it's concave up. Where does it seem to be changing concavity? Right about 0. Right, it's supposed to be. It's my graph center, my drawing center. Okay. On what interval is, now you gotta be careful with this. Part C, this is a little tricky. On what interval is f prime an increasing function? So we want to know.
And then the next one is 0. Double prime is 0.
Where is f prime increasing?
When it's positive.
When what's positive?
X.
Yeah. Because an increasing first derivative, the rate of change of the first derivative is the second derivative, right? That's what it means. First derivative is the rate of change of the function. Second derivative is the rate of change of the first derivative. So where the first derivative is that what we're asking here? We want to know where is the rate of change. Where is the rate of change? So where is the rate of change of the first derivative positive? Where the second derivative is positive, which is going to be there. Okay? Meaning, think what that means. Now let's connect that to what that means as an ant walks along the curve. As an ant walks along the curve, that just means that the slope is always increasing, right? That's here. As the ant walks along the curve, the slope is moving from being very negative to less negative to 0 to positive to positive to more positive to more positive forever.
Positive infinity.
Right? It's always getting bigger. The slope's always getting bigger. Okay, last question. For which value is f prime of x a minimum?
X equals 0.
Correct.
Right. Exactly. Does that make sense? That's the steepest that this thing is going to get, steepest negative slope it could have. The slope is getting more negative, more negative, more negative, and that's where we hit that inflection point, and it flips around and it starts to, the rate of change, the slope starts to increase. So that's going to be where it's at its minimum.
For what value of x is that minimum?
Yeah, so at x equals 0, that's when f prime, when the first derivative is going to be at its lowest level. Right? Now let's just, for grins here, let's just graph the first derivative roughly. We know it's going to be 0 there, right? We know it's going to be 0 there because those are places where I have horizontal tangent lines. Right? We know that over here it's positive, in here it's negative. So isn't it just looking like this?
Wait, how's that make it positive over there?
Because
It's above last.
yeah, makes sense. Because here, from this point on, the ant is walking uphill, an increasingly steep hill. Over here, the ant is walking up a decreasingly steep mountain until he hits the top, where it flattens out and the slope is 0. Now the mountain is getting increasingly negative, the slope, right? Until it gets to about there, and at that point, it starts to curve up again, right? Make sense? So that's where the slope is the most negative, right there. You can see that. That's the vertex of that first derivative function. Okay? Okay, good. Now move on to some real problems here. How about that first block? Pick a problem from 7 through 24. How about it? You pick.
That was 11.
I mean 11 through 24, you're right.
We do 15.
Okay, I'm hearing lots of different ones.
Uh-oh.
16. 15 or 19?
Can we just pick 4?
No, what you're supposed to do is you're supposed to go 11, 15,
Why don't we just
19,
do that then?
23.
Yeah, we
every
just
four.
start with 11 and then.
Yeah, why don't we do 11, then 15, and then 19, and then 20?
I'm not going to do them all, but I will.
You specifically said let's do them all already.
No, I'm not going to do them all. I meant the ace of the test.
Okay.
Okay, but I will do some good examples. Okay. How about?
We do 11. Or up.
13. I mean 15.
Okay, 11's easy. We'll do 11. Okay, now our goal here is to, what are we doing?
This 11 is completely different. This is too
Calm
many.
yourself.
Just follow this one.
Is yours, you mean Matt's is different?
Yeah.
Oh, okay, well this is our 11. I would do this one. Okay, so They want us to find domain range, asymptotes, intercepts, relative extrema, and/or points of inflection, symmetry, all that good stuff. Okay, so we got to find everything.
I like that.
Okay, I've looked to see that's going to cause a problem here. So. And he's like, oh well.
He's like, yeah.
Just sitting in the
Okay, original function. Any issues with the domain? Any places where the function's undefined?
No.
No. We know that because there's no x's on the bottom, no even roots, so we're fine there. Domain is all reals. Good. So we can move on to the first derivative then. What's our first derivative?
9x squared.
Minus 9.
Okay, so there's our first derivative.
Wow.
We could factor out a 9, right?
We could. One.
Right, if we want to. Okay. We could factor that if we want to, right?
Well, you could.
So that becomes 9 times x
Plus
one. And then if we want to set that equal to 0, we can find, we need to find all the critical numbers of the first derivatives. The places where it's 0 and undefined. Nowhere is it undefined.
Nowhere.
But where does it equal 0?
Plus or minus 1.
Aha. Aha. So those are our critical numbers, plus and minus 1. Okay? So we got first derivative critical numbers. While we're at it, let's calculate the second derivative. We need to get inflection points. We would anyway. It's such an easy thing to do. Now, where do we want to differentiate here? Where do I pick up? These are all different versions of the first derivative. Which one do I differentiate? There you go. Yeah, the easiest one. So we'll go straight down. So what do I get for my
18x.
Okay? And that's 0 when?
When x is 0.
Okay? So there's our second derivative critical number at 0. Okay? So we got 3 special points, 3 total critical numbers. Let's throw those on our table and see what happens.
Is that CN2?
Yeah, second derivative critical number.
Like a subscript.
Well,
That's a fairly straight line. So is that. You're getting good at these lines, right?
Yeah. Okay, let's put one more. Okay, so. Okay, so here's our x's. F prime, F double prime. So we had critical numbers at plus and minus 1. So -1, +1, and at 0. Right? Okay, at 0 we had a critical number of the second derivative, so like that.
Wouldn't 0 be a critical number?
It is. Of the second derivative.
Oh, okay.
First derivative critical numbers were plus and minus 1.
Why did you put 0 next time?
Because those are the zeros at plus and minus 1. That's where the first derivative equals 0, right? At x equals 0, that's when the second derivative equals 0, right? Make sense?
Yes.
Okay, so then what do we want to do here? How do we proceed on our table? We'd rather work as far down the table as we can.
Which is the first row of critical numbers?
Say it again.
The first row of critical numbers.
Right. These are the x values, and we may put some other values there later if we need to also. Okay. Good. We'll check the concavity. The thing is, we have a second derivative. Let's check the concavity at the first derivative critical numbers, at the zeros of the first derivative, right? So here we get a horizontal tangent line. We get a 0 of the first derivative. What's the sign of the second derivative? F double prime of -1 is what? Positive or negative? Negative. Okay, so what's that tell us? A horizontal tangent line. Yeah.
Okay, hold. How did you get negative? You plug in -1.
Right. We wanted the second derivative test asks us to evaluate the sign of the second derivative.
Okay, and the sign determines the concavity.
Right.
Negative.
Right.
The negative
Yep.
concavity.
So negative
Then positive.
Unhappy function, frown. Okay, what about it at 1?
Why don't we just write like 18 on the other things and what's positive?
Why- Well, because we don't need to. If in this case, good question. Yanya's question is, why don't we write an 18, negative 18, and positive 18? Because the only part we care about is the sign. Yep. And then in the future, they might be really ugly numbers, and we're just finding the overall sign of the products of the factors. We don't care what kind of ugly number it is. Okay. Okay. So then let's see if that's positive and that's negative. What is that?
Negative.
Okay, that's a 0 of the second derivative. No, hang on. What's a 0, a transitional point of the second derivative? If I'm going from inflection point. Yeah. So that's an inflection point. Okay. Good. Yes, sir.
So the other day, didn't you say that might be an inflection point, like, as you weren't too sure?
That was different. The other day.
But I was wondering what the circumstances are that you aren't really sure when it's not.
Okay, you're not sure. If I get critical numbers of the first and second derivative that line up, then it's indeterminate. And then I got to figure it out. But this time, notice that I got a 0 of the second derivative that doesn't line up with the 0 of the first derivative. And even if it did, the definition of an inflection point is this. If I'm transitioning from negative to positive or vice versa, that means inflection point. Okay? All right, so what else do we need here? We needed, how about if we find out, okay, I got too much talking. We need to sketch it, right. Okay, there are no vertical asymptotes, right? No horizontal asymptotes because it's not a rational function. So now we could just sketch it. If they want us to anchor this thing, we could plug in, let's put in at least one value. When x equals 0, y equals 1, right? So we get the point 0, 1. Because if I plug 0 in for x in my original function, I get 1.
Oh, okay.
Okay? And so now we can just sketch it. So now we get... So at 0, 1, right there, that's our inflection point. And we're going to be... Yeah, I'll just sketch it. So it just goes like this then, right? Something like that?
The inflection point is at 0 still. Okay.
It's at 0, 1.
Okay.
Right? Does that make sense? Okay. Now, what about symmetry? Let's look at the symmetry stuff real quick. And this isn't as big a deal, but worth talking about maybe. We can see graphically, does this thing have folding symmetry about the y-axis?
Yeah.
Yes, it does.
This way?
Oh, no, not that way.
Does it have rotational symmetry about the origin?
Yes.
No, it doesn't. Now, it could have. If it had been shifted down a little bit, it might have. But it doesn't now. If I rotate the graph 180 degrees, this is going to get shifted down here, and it's not going to look the same. So it does not have even symmetry, which is folding symmetry about the y-axis, or odd symmetry, which is rotational symmetry about the origin. How could we have known that? Well, go ahead, Ray.
I said it does on the y.
It does on the y-intercept, it might, yeah. Okay, how could we have known that? Here's how you can tell. There's a good shortcut for this. Remember, we have a test for symmetry. If I plug in negative x for x, depending on what happens, that's going to determine the symmetry. If I plug in negative x and I get the very same answer back that I started with, then that's even symmetry. But that's not going to happen, is it? If I plug in negative x, the quantity negative x cubed makes that term negative, doesn't it? If I take a negative number to an odd power, the sign is negative. Same thing there. So those two terms would have switched sign, but the one would have stayed the same, wouldn't it? Right? So it's not even and it's not odd. If all the signs had switched, so everything was negated, was turned opposite, then it would have been odd. If none of them would have changed, it would have been even. There's a way we can tell, though. With polynomials, here's where the words even and odd come from, in case you're wondering. They come from the exponents. I've got x cubed minus 9x to the 1 plus 1x to the 0. A constant is really the 0, that's the coefficient of the 0 term, right? Does that make sense? So look at the sign, look at the exponents. Look at their, are they even or odd or both? Well, these two are odd and that one is even. Because they're mixed, the symmetry is neither. If they were all even, it would be even without even checking. You know that. If they're all odd, it's odd. Okay? A quick way with polynomials of knowing. All right. Good. Okay, let's look at another one. How about? Oh, good. I'm gonna do 24, which is like 23. Okay, this is a good one, I think, because it's got a rational exponent. We got to know how to deal with those. Okay, so first things first, domain. Do we have any issues with the domain?
2/3.
Okay, yeah, we got. Here's the question mark, right? What's going on with him? No x's on the bottom, so we don't have to worry about dividing by 0. But I've got a 2/3 power. Remember, I can't take an even root of a negative number. So the question is that an even root or an odd root? Which one? It's odd. How come? You're right.
Over 3.
Odd.
Because the 3 is odd, the denominator's odd. It's a cube root. It's an odd root, so we have nothing to worry about. No place where the domain is weird. Okay? All real numbers.
What about the other ones?
Okay, but now that's not the
2/1, so it's an odd root as well.
right. So this one here.
Never mind.
Okay, that one's okay because it's not a fraction. This one and the 2 on the top doesn't matter. It doesn't matter if it's even or odd. It matters, but it doesn't matter. It determines. It's going to change the shape of the graph, obviously, but it's not going to. Oh, yeah, but the top being even has nothing to do with what kind of root that is. It's an odd root because the index, which is the denominator, is odd. Okay, so we can move on to the first derivative. Okay, so what do we get? First derivative time.
2/3 x over minus or to the 1/3.
To the minus 1/3. Good. Okay. Take the power down, subtract 1, minus 2x. Let me write that better. That's kind of messy.
Plus 10 zeros.
Minus. Okay, so there's our first derivative. Now we gotta do something with that. We're gonna have to figure out where the critical numbers are. Okay, so to find out where the critical numbers are, let's rewrite this thing. Let's rewrite it as a fraction. Okay. So this is really going to be. Couldn't we rewrite that as 2/3 times x to the 1/3? Okay. So if that's y prime, let's find the critical numbers. Now, are there any places? Let's always look first to see if there's any places where the derivative would be undefined. Any danger zones there? Yeah, we got an x on the bottom. So when would, I've got an x on the bottom, so here's a red flag right here. Right? When is what value of x is going to make the denominator 0?
0.
0. Sure. When x is 0, the cube root of x is 0, right? So x can't equal 0. That's a place where we get a first derivative critical number. So y prime is undefined at x equals 0. Critical number. Okay? Now, what we got to find where, if and where, the first derivative equals 0. Okay, so let's do that. If I set this equation equal to 0, so 2/x to the 1/3 minus 2x equals 0. So now talk me through that. What do I do if I want to solve that equation? What do I do? A couple things I could do. What do you recommend? What's that? Okay, add 2x, good. Why not? Let's push the 2x to the other side. So we're going to end up with 2 over 3x to the 1/3 equals 2x. Now what? Now what do I do with ratio equations like that? I could. A couple things I could do. I could have up here, both good options. You take your pick, really. I could have written this as 2x to the 4/3 over, actually 6x to the 4/3. You could have multiplied top and bottom by 3x to the 1/3. That's fine. Okay, that's fine to do. If I do that, in fact, what's that going to look like? If I were to do that, I would have gotten. Everybody see that? Oops, 3. If I multiplied this one by 3x to the 1/3 over 3x to the 1/3, 2 times 3 would have given me 6. X to the 1 times x to the 1/3 would have been x to the 1 plus 1/3, 4/3, right? And then I have my common denominator on the bottom. That's okay to do. Now, when is that fraction going to equal 0? Say it again. When the denominator is 0. Good. So if I set the denominator equal to 0, I'm just solving that equation. Now look what happens if I cross multiply down here. Just watch what happens. If I cross multiply, notice that I'm getting 6x to the 4/3 equals 2. Same thing, isn't it? Right?
Wait, did you say when the denominator is 0?
When the denominator is 0 is when the derivative is undefined. We already found that. We could see that right away. That we had an x in the bottom. Okay. We could also see it here if we wanted to. Okay. But my point is, these are really, in my mind, equally good ways of doing this. It doesn't matter. For consistency's sake, maybe you want to do it that way. That's fine. If we want to write this as a ratio, what's consistent about that is we always know to set the numerator equal to 0 to find these kinds of critical numbers, right, where the derivative equals 0. Set the denominator equal to 0 to find where the derivative is undefined. So we get both species of critical number that way, right? Either way you do it, though, if I just solve this by cross-multiplying, either way, I'm coming up with the answer. What? X equals, if I divide by 6, I'm going to get 1/3. X to the 4/3 equals 1/3. So what's X? This is a little tricky. If X to the 4/3, you got to think about this now. Think what this means. X to the 4/3 equals 1/3. If I were to write this as a radical maybe in an exponent, x to the 4/3, isn't that the same thing as saying x, the cube root of x to the 4th? Right? Okay. So if I cube both sides, that's okay. That's going to give me x to the 4th equals 1/27. But what do I have to do if I am solving, if I'm taking an even root of both sides to solve an equation? I have to have a plus or minus in there, don't I? Now, I want to show you where we're going to see that without having to write it this way. Everybody agrees now when we do it this way that this has to look like x equals plus or minus the 4th root of 127. Right? Those would be my critical numbers. How could we have seen that right here? Here's how. Because the top is even. Right? So to undo the top, I would have to take both sides to the 3/4 power. Right? Taking both sides to the 3/4 power amounts to a 4th root. Right? So doing this process, taking both sides to, whoops, I'm going to go to the next page. That's going to get too messy.
Yeah.
So, that's what I have, right? What was it?
X to the 4/3.
Oh, 4/3.
Because the top was even.
Oh, sorry. Yeah, you're right.
First thing I need to say, I'm in trouble.
Okay, think of the step I would have to do to unlock the x. I'd have to take both sides to the 3/4, and that means even root. So I need a plus or minus.
Oh, what about all the other steps you did?
Well, we didn't have to. That was my point. We didn't really have to do that. We wrote this as a radical to the power, right? Or power of a radical. And then we could see pretty plainly we needed the plus or minus, but my point is just that we never had to do that. We could have just instead taken both sides to the 3/4 power. Okay? And so we know then that these cancel. Right? That makes sense? If I take a power to a power, I multiply the exponents, and 4/3 times 3/4 is 1. So I'm going to get x equals plus or minus, because those are even, 1/3, 3/4. That's my answer. Okay. That's just going to give me some decimal. If I put that in the calculator, I'm just going to get a decimal.
Yeah, you are.
Less than 1.
And what is it roughly if I put it in the calculator? I'm just kind of curious. Plus or minus roughly what? Something bigger than 1/3, but 0.4 to 4386. So 439. Okay, so we got our critical numbers then, and we'll just put them in as decimals. So we end up with x equals plus or minus 0.439 roughly as decimals. So those are my other first derivative critical numbers. Now let's collect all those into a table. So we got these, and we got this guy, 0, right? So far, if we're building a table, just keep track of this. We got our x's, so we had at x equals 0, we had an undefined first derivative. At x equals roughly plus 0.439, is that what it was?
Yeah.
We had a 0 first derivative. At negative 0.439, we had 0 first derivative. Okay, 3 critical numbers. Okay, now, important question to you. Going back to this ugly problem here, if I didn't need inflection points, would I probably bother taking a second derivative? No, probably not. Probably not. Because it's not a super easy derivative to do. So we would use the first derivative test. If all we needed were extrema, we would just use the first derivative test and pick test points and just test, see what's going on. Okay, but we do, turns out, need a second derivative. Well, let's calculate it. Okay, 8. Quiet. Okay, what about this second derivative? What are we going to get?
Negative 2/3.
Negative 2/6.
Negative 2/6.
Negative 1/3. X to the negative 1/3.
What's my rule? I bring down the power, the exponent.
Negative 2/3.
Negative 1/3 times 2/3 is what?
Negative 1/3.
No. Negative 2/9. Multiply, right?
Yeah. Yeah.
X to what?
Oh, we're multiplying fractions.
4.
Yeah. Okay. Negative 1/3 minus 1 would be negative 4/3. And then this term?
Negative 2.
Okay. So we want to find then, now are there any places here? No. Now here's the question. You got to listen very closely to this one too, because this is a hugely common mistake, and it's easy to make this mistake over and over again. Because you got to get this one into your brain. Are there any places where the unique places where the second derivative is undefined? In other words, are there places where the second derivative is undefined where the first derivative is not undefined?
How the heck are you supposed to know that?
We know that because, look, we already know that the first derivative is undefined at x equals 0, right?
Yeah.
Okay, now I want you to notice something in the behavior because you can learn something important about functions. Where is this? If I were to write this as a fraction, and I can, I don't have to, but I can. If I write this as a fraction, I put in the negative power on the bottom. Y double prime equals negative 2 over 9x to the 4/3. If I put that negative exponent on the bottom and make it positive. So where obviously then is the second derivative undefined?
0.
X is 0.
Yeah. Right? I've got an x on the bottom, but wouldn't you agree that the bottom is going to be 0 when x is 0? That's what's going to make that denominator 0. Okay, now notice that the second derivative inherits that discontinuity from the first derivative. That's always going to happen. Always. If you continually differentiate a problem, wherever you first time you get an undefined derivative, from then on down, if you were to take 100 derivatives, every 12, it's going to go away pretty soon, but actually this one would. It would always have an undefined nth derivative at that place. And so really it only counts for the first derivative. Okay? Okay, what else now? So if I want to find out where this equals 0, we've got to find the other critical number. Where does that equal 0? Let's just do the cross multiply thing. How about? Okay. So if I add this to the other side, don't I just get this? Don't I just get 2 over 9x to the 4/3 equals 2?
Wait, but I thought we already put like x is 0. Is that wrong? So we find the 0.
We got to find the 0. Yeah.
Equals positive.
There we go. Yeah. Okay. Ran out of time. What am I going to do here though? Multiply by 9/2, get some number, and then just take
Read that shit?
cross multiply. And I'm going to right exactly. I'm going to end up taking 3/4 power, which is an even root. Yeah.
Okay, we totally messed up all these chairs.
All right.